Hello, my name is Alistair Hales, a postdoctoral research associate based within the Electrochemical Science and Engineering Group at Imperial College London. Today, I'm going to present an overview of my most recent work on the cell cooling coefficient. I'll begin with a background on lithium-ion heat generation and temperature-dependent performance before introducing the cell cooling coefficient concept and presenting our recent experiments. I will use the results to evaluate the relative performance of surface cooling and tab cooling in pouch cells before summarizing our conclusions and outlook on the state of the industry. It's worth noting that all work that I present today is taken from our most recent paper, published in December 2020 in eTransportation. Heat generation occurs in any lithium-ion cell, and it is dependent on many operational characteristics that are highly nonlinear. Operational temperature, the rate at which the cell is being charged or discharged, and the cell's state of charge all impact instantaneous rate of heat generation. This all matters because temperature gradients are induced in the cell as heat is rejected from its volume. Temperature gradients lead to unequal current flow in a cell, and this accelerates degradation. A key aim in the design and use of any cell should be to minimize temperature gradients occurred across the cell, because this will maximize lifetime and performance. Battery pack designers select the cell based on the performance metrics that are available to them. There is no metric which defines thermal management capability, so they end up choosing cells with the best energy density, which you'll find on almost any data sheets. And so cell manufacturers choose to maximize energy density in order to remain competitive within the market. This is a problem for thermal performance because active material is very thermally insulating. Temperature gradients and therefore degradation will be greater in a more energy dense cell. Battery pack designers attempt to combat this problem with over-engineered thermal management solutions. They are heavy and demand lots of power. Only 64% of the Tesla Model 3 battery pack is lithium-ion cells, and the thermal management system makes up most of the remaining mass. At cell level, energy density may be optimized, but at pack level, it's certainly not. What we really want to know is what temperature gradient would be required across our cells to remove a certain amount of heat. And so the cell cooling coefficient is designed to provide exactly this information. We divide the rate of heat rejection from the cell by the temperature gradient occurred across the cell, and we believe that the cell cooling coefficient can be used as a tool to estimate rate of heat rejection for a given thermal gradient, a constant for a particular cell and surface to be managed, a metric against which any two cells may be compared, and a standard for competition and improvement amongst cell manufacturers. Cell cooling coefficient is empirically derived, and this demonstrates one of the key benefits over established methods for defining thermal performance. Both the Beer number and thermal conductance actually define a body's capability to transfer heat from one point to another, and this is not at all relevant for a device that is generating heat from throughout its own volume. We would need to know all of this information before we try to quantify the thermal performance of a tab-cooled or surface-cooled cell. However, with the cell cooling coefficient, we are able to reduce it to just this table, much more manageable and much more likely to appear on data sheets in the future. In the presented study, we wanted to evaluate the varying cell cooling coefficients when the geometry of our pouch cell was changed. We used 5 different cells, which we believed were identical other than their thickness. The thicker cells have more layers. In a teardown, we confirmed our hypotheses. Each layer in each cell was identical, and we were able to ascertain that, based on beginning of life capacity, each layer could be attributed to just under 50 milliamp hours of capacity. We also discovered that 2 of the cell models, the 3200 and the C4000, 3.2 amp hour and the 4 amp hour cell respectively, had thinner tabs. This was a bonus, giving us another geometric variable which we could look at, and there's a little bit more on that later on. Geometric variation affected the surface and the tab cell cooling coefficients. Tab cooling performs better, cell thickness is increased, and this is shown in the bottom left-hand side. We'll look at this more later on. For now, we'll look at surface cooling, which is shown in the bottom left-hand side. Sorry, tab cooling on the bottom right-hand side. And we see that with surface cooling, surface cooling performs worse as cell thickness is increased. This was expected. A thicker cell means a greater distance over which temperature gradients can build up, and all of this leads to a reduced cell cooling coefficient. Cell cooling coefficient does not tell the full story because it's not unable to account for the expected heat generation rates. Each layer is equally rate capable and identical. Therefore, we made the assumption that operational heat generation rate scales in proportion with cell beginning of life capacity, i.e. more layers equals more capacity and therefore more heat generation in expected operation. With our per capacity coefficient, essentially dividing the cell cooling coefficient by beginning of life capacity, we are able to account for expected heat generation rates in our particular test cells. The consequence gets even worse for surface cooling, and across the range we tested, the per capacity coefficient is reduced by more than half as thickness is increased. This highlights the reasons behind the current generation of lithium-ion pouch cell design. We cannot have thicker cells, which would lead to better battery pack energy density, because we are unable to cool them effectively, and we're stuck with large, flat, and very thin pouch cells until we stop surface cooling in battery packs. As previously discussed, two of the cells had thinner tabs. This is clear in the graph, and the actual thickness reduction is shown in the top right-hand table. The effect on energy density is shown in the bottom left table. By increasing the thickness of the tabs, we reduce the energy density by less than 1%. The benefit in terms of thermal performance is substantial. We calculate that the tab CCC would increase by 20% for the 3.2 ampere cell and 17% for the 4 ampere cell if thicker tabs were selected. So for a 0.7% reduction in cell level energy density, we increase the thermal performance by 20%, which isn't such a bad payoff. It comes back to optimization of pack energy density rather than cell level energy density without consideration of the pack. Tab cooling can be enhanced by thickening the tabs of any cell, and a thicker electrode stack benefits tab cooling because it increases the cross-sectional area through which heat is removed. Therefore, tab cooling is theoretically unlimited by cell thickness. This is great for modular prismatic designs that are beginning to dominate the R&D presentations at conferences. We strongly believe that tab cooling has potential to significantly advance the battery pack design industry. Yes, it throws up complications with actually implementing the thermal management onto the cell because the tabs are also required for the cell's electrical connections. However, the battery industry is expected to triple this coming decade and grow 10,000% in the coming 30 years. So this is a problem well worth sorting out right now. There's no downside. The incremental advances in cell chemistry can continue to trickle down to the end user, regardless of how the thermal management strategy is implemented in the battery pack. The flowchart on the right-hand side follows the same format as one presented earlier, but instead presents a potential if thermal management is considered at every stage of battery pack design. This doesn't necessarily mean tab cooling. Increasingly, we are seeing cycle battery packs in EVs. The iPace and e-tron are just two examples. But it does mean quantification of thermal performance, and this is where we believe the cell cooling coefficient is the perfect tool for communication within the industry. Thermal management can no longer be ignored in favor of energy density optimization. Cell designed to be thermally managed will have a slightly lower energy density, but this can be made up many times over at pack level with more effective thermal management systems. Furthermore, a cell designed to be thermally managed will incur smaller temperature gradients, and this will reduce the degradation rate of the cell over its lifetime. The work and outlook I have presented today grew into the TopBat project, which looked at using the cell cooling coefficient alongside equivalent circuit models to optimize the geometric design of a pouch cell. A presentation on that topic is available on the Faraday Institution website. Thank you very much for taking your time to listen to my presentation today, and I am always available for any questions.